All right. So thank you. Well, just before I start, as there was a question from Mark last time, and I forgot to tell you about these things I was planning to tell you. So the question was whether this random walk condition to stay positive on a positive half-line. So let's call it X. And had whether this random walk is transient or recurrent. So the original random walk was recurrent. It has zero mean, so it's going to fluctuate between minus and plus infinity. The nice thing about this random walk is that this is in fact transient. Okay, so that's a transient random walk, and you can actually work this out by just computing the expected number of returns, or you can compute the expected number of returns to some interval y plus 1, so it should not be very hard if you use duality, and then you will see that this is a finite number, and actually this should be uniformly bounded over all y. Okay, so that's one fact, and that's basically a very common situation. So if you have an unbounded domain, and if you somehow condition on the process to stay in this domain, then most likely the process will go to plus infinity. So because of this pressure from the walls of the domain, so you can think about this. Okay, so today I will start a new topic, and somehow if you didn't understand a lot in the previous section, then it's your chance to start from scratch, because there will be not so many intersections with the previous part. So what I'm going to talk about, random walks in cones, and basically the question I will be looking at is the question of the asymptotic behavior of a random walk started at some point x in cones. So I'm going to look at two-dimensional situation, but in fact the same approach will work in the multi-dimensional case, and in the paper which I will be discussing, we were considering this multi-dimensional case. So this approach is based on some kind of universality idea. So universality means that we are going to somehow approximate random walks with the Brownian motion, and for that reason I just want to discuss what is known about the Brownian motion. So that's the very first step that we need to take. So first, let's just fix the cone. So what I'm going to look at, we will consider two-dimensional trees. Okay, and well, one of the reasons is that some of the computations are more explicit. Now what we can do, so I'm going to start with the Brownian motion, so let's fix the cone. So this is my cone. Okay, so let's call this x1, x2, and then if this angle is alpha, then my cone K in polar coordinates will be eta such that modulus eta is strictly less than alpha. So that's the cone. Well, in principle, for the Brownian motion, it doesn't matter what cone we are going to take, because we can always rotate Brownian motion, and So if our original Brownian motion was the standard Brownian motion, still we are going to get standard Brownian motion. Okay, so that's the cone. Now the exit time. So the exit time I'll be looking at is firstly the exit time for the Brownian motion. So our x dm is the first time t greater than 0 when x plus dt does not belong to my cone k, where b of t is two-dimensional standard Brownian motion. This also will not be I'm not going to prove much in this situation. Now what I can say is that one can find an explicit expression for probability that tau x greater than t. So I will give you this expression shortly. And also, and even for and even for the hit kernel, p k t x y. So basically that's the density. So if you start at x, the Brownian motion x plus bt belongs to dy, and you haven't exited the domain yet. Okay, so there are explicit expressions for the hit kernel and for the exit time. And basically, well, if you know the hit kernel, of course, you can just integrate it, and then you're going to get an expression for the tail of the exit time. Okay, so now, in order to give these expressions, so they are given in terms of harmonic functions. Okay, so basically what happens is that in order to give the answer, so we should solve the following equations. That is by the solutions to the following problem. Delta Laplace u equals 0 when x belongs to k, and also on the boundary u of x is equal to 0 when x belongs to the boundary of this domain. Now, because of the form of the domain and because of the nice scaling property of the Brownian motion, so that what we can say is that these solutions should be homogeneous. Okay? So they should be homogeneous, and again, if we use notation r theta, so the solutions we are interested in are of the form u of x is equal to r to the power E times some function d of theta. So that d of theta can be found, in fact. So when r theta polar coordinates. Okay, so we are taking this two-dimensional point x, then if x is not equal to 0, so we can just write it using the polar coordinates, right? Okay, so now if we start looking for the solution in this form, then what we need to do, we need also to rewrite the Laplacian, right? So Laplacian in polar coordinates. We'll have this form. Okay, so what I'm discussing now, how we can solve this equation in order to obtain the countable set of interesting solutions. And using this set, we are going to write down an explicit expression for the. Okay, so now in polar coordinates we can write delta as d squared over dr squared plus 1 over r d over dr plus 1 over r squared d squared over d theta squared. So that's the expression for the Laplacian in the polar coordinates. Now if we use this expression, what we are going to get. Okay, so let's just plug in our function of this form, which is homogeneous in R, and then we will get E times P minus 1. Okay, so delta U is equal to E times E minus 1 R to the power P minus 2 U of theta. So this is the term coming from here, plus from here we will get R P times R P minus 1 from here, and when we divide by R we're going to get minus 2, and nothing is changing.
V, it was V of theta, no?
It's V, yes indeed. It's V. Okay. This is V. And finally here I'm going to get R to the power P minus 2 V double prime of theta. So this should be equal to 0. Now the nice thing is that you can see that all R can be cancelled, and what we are going to get is the expression V double prime of theta, and here I will have P squared minus P plus P are going to give me just P squared V of theta, so this must be equal to 0. Okay, so that's the first bit. Now our U must satisfy this equation as well, which means that basically R to the power P V of theta is equal to 0 when theta is equal to plus alpha or minus alpha. Right? So we have two boundaries. So if you plug in theta,
don't care about the 1 point r equals 0 because that's never going to happen there.
Okay, so we don't care about this. So can we erase this? Okay, so this equation is not hard to solve. That's second order ordinary differential equation with two boundary conditions, and the solution to this equation is given by cosine function, right? And because of the boundary conditions, there will be some restriction on the cosine functions. Right? So basically, let me just write down the solutions. Somehow, if you look at this, this is nothing else but equation for eigenvalues, right? And with the prescribed boundary conditions. So we have a countable number of solutions. Solutions are given by B and theta equals cosine E and theta when Pn is equal to E over 2 alpha times n, and then we change it from 1 to plus infinity. Okay?
But then you have got multiplicative constants as well, right?
You mean you want to multiply this by some number?
No, of course.
Yeah.
If you say it's countable number of solutions, it's not exactly true.
Yes.
Up to a constant.
Up to a constant. That's true. So if you multiply, so these are basically eigenfunctions that we are interested in.
And plus identical 0, of course.
Plus identical 0, in which we are not interested at all. Alright, so it doesn't give much. Okay, but it solves this equation as well. So basically, we have a countable number of interesting solutions, and then using these interesting solutions. So first of all, let me comment about the first solution. So that's the most important one. So for the first solution, V1 of theta, so this is cosine E over 2 alpha times theta. Right now, what you can see is that when theta changes between minus alpha and plus alpha, so if theta is equal to minus alpha, we're going to get cosine E over 2 here, and for theta equals alpha, you're going to get cosine E over 2, and between them, this solution is always greater than 0. Okay, so this function, so this is a positive eigenfunction, so that's strictly greater than 0 when theta is such that modulus theta is less than alpha. Okay, so this function is greater than 0, and the corresponding function u1 of theta, which is equal to r to the power p1 v1 of theta greater than 0 for x belonging to cone. Okay, so this function is strictly positive inside the cone, it is equal to 0 on the boundaries of the cone, and it solves the Laplace, well, it solves this equation, Laplace u equals 0. Okay, so basically, now once we have these functions, now I'm ready to write down the solutions. Okay, so exact solution, exact formula for probability that tau x is greater than t is given by this nice infinite series. That's the sum from n from 1 to plus infinity. B n times modulus x squared over 2 times t to the power d n over 2. Okay, so that's one thing. Now you multiply this by a special function f11 d j over 2 d j plus 1 minus modulus x squared over 2 times t. Okay, so these terms do not depend on theta, so as you can see that they depend only on r. Okay, so they depend on the distance, and we multiply by finally by our eigen function b j of theta, where r theta is our polar coordinates of x. Okay, so that's the expression. We don't. So f11 is well, I can write this down. So it's a confident hypergeometric function, and it can be written as f11 a b z is equal to 1 plus a over b z over 1 factorial plus a plus 1 divided by b plus 1 z squared over 2 and so on. Also, you can write down the constants. Bn is equal to gamma Tn over 2 plus 1 divided by gamma Tn plus 1 over 2 times 2 sine pi and theta over theta.
So sorry, for their functions, factorials, yep, in the denominators.
Just a second, no theta out, of course.
Yep.
Sorry?
For the f function,
Yes.
hypergeometric should be factorials everywhere.
Well, so this function will not appear. So that's just an illustration of what we can get. Also, well, we can write down an explicit expression for the heat kernel, but we don't really need this explicit expression.
Sorry, does it matter whether the cone is convex or not?
Well, here it works for non-convex cones as well, so that there are some regularity assumptions about the boundary of the cone. But in general, it works for non-convex cones.
So you can have alpha greater than pi over 2, right? That's my question.
Well, in 2 dimensions, yes, you can have alpha greater than.
Is it possible?
Have it greater than pi.
Yeah, it's over the top. Yeah.
Well, I'm not even sure whether you can have just one line, so this I don't remember.
Don't distract, Mark. You're just asking impossible questions.
I don't remember whether you can have this kind of situation when it's just a straight.
Go to the Riemann surface and keep working there.
Well, okay, so, but the thing is that.
Sorry, Denis, is it possible very quickly to indicate how do you get these results from the harmonic function behavior? Why is it so? Very quickly for the benefit of our students.
Well, basically, what happens in this paper, so they actually do not derive this exact result. So they derive, so they find an expression using these functions for E k, t, x, comma, y. So they found this expression, or somehow, I guess they were solving for this expression using separation of variables. That's what's happening. But what they did, they just write down this infinite series, and then they just checked carefully. The first thing that they checked is that this function solves the heat equation, and it disappears on the boundary. So somehow, so that's the very first thing they check, and they also check several regularity properties. So somehow they look at this problem not as a problem in probability theory, so this is just a problem of solving a Kolmogorov equation. Okay, and because this domain is nice, and because Brownian motion has this nice scaling property, it is possible to do this. Again, because when you do separation of variables, then very often that's more or less Fourier method, so that's how those eigenvalues will come into place. So that's some vague description of what happened in this paper. But well, as long as you know that you can do it, I guess it's not very hard to do it, so the most difficult thing is believe that you can do it. Okay, so now from this expression, so actually for our approach we used this explicit expression as well, because we needed some bounds for our exit times. But basically what we will need today is just the fact that from this infinite series you can write down asymptotics for probability that tau x greater than t. And it's not hard to guess what this should be. So basically the very first term is going to give you the right asymptotics. Okay, so we can pause. So we can obtain, so given this explicit expression, we can obtain asymptotics for probability tau x greater than t. So basically, so what we are going to get is this expression as b1 of theta, so that's the first term, times modulus x squared over 2 e1 over 2 t minus e1 over 2 as t goes to plus infinity. Or we can write it, so if you combine these two terms together, then basically we can write it as some kappa, some constant kappa. Now this will be our function u1 of x. So u1 of theta times modulus x squared t1 will give you exactly the function u1 of x. So now polar coordinates are going to disappear, and divided by P1 over 2 when t goes plus infinity. So that's the most essential part. That's the part that we are going to use. Now, in the rest, so I will denote. I'm not going to use all other eigenvalues or other eigenfunctions, just the first one. So I will denote P1 as P and U1 as okay. So that's so these are the prerequisites that we are going.
Sorry, Denis, the fruit of collective wisdom, we suspect that Pj's and Vj in the sum for the tail should be n, Pn's and Vn. Is it correct?
Right, so here it should be Pn indeed.
And V as well.
And Vn. Yes.
Sorry, what's that before the U1x in the last line on the left?
Kappa?
Oh, kappa, yes.
Looks like kappa.
Kappa.
Okay.
Kappa. Okay, so that's this probability. So we can before moving to random walks, I will make one more comment as well. So basically here we can recall an interpretation of harmonic function probability. So the fact that U is a harmonic function means that U of Bt is a martingale, and basically we can also talk about, sorry, I forgot, it should be Ux plus Bt. Ux plus Bt indicator tau x greater than t is martingale. Well, basically, so why do I need this indicator? U has been defined only inside the cone. So well, here in two-dimensional case, U is defined everywhere. So then U of Bt is a martingale. In general, it is sufficient for us in d-dimensional case to define U only in the cone. So here U of x plus Bt is okay as well. So it's a martingale, and basically we can perform loops H transform. So very similarly to the previous lecture, and to define Brownian motion conditioned to stay in concave, right? So basically, well, just to remind you, so what we need to do for that, we just define the transition probability is hat by defining transition probabilities. P hat P from x to y, so that's just going to be U of y divided by U of x times P T P K T X comma Y for all X Y inside the column, right? And the fact that this is a martingale and U is strictly positive, so this will ensure that this is a nice transition. At least positive transition function, which is summable to 1, but you can also show that this is indeed a transition function and you will have Kolmogorov equation and so on and so forth. Okay, so you can define Brownian motion condition to stay in the column, which will be useful for us as well. Okay, so that's okay. So these are all preliminary things that we need. So I can move on to a random box now. Okay, so that's gonna be section 2.2. So any questions so far?
The last thing here, it's asymptotically equivalent or just equal in the last line?
Asymptotically equivalent here.
Yeah, but the next one, below it, where kappa is.
Well, you can write this as equal, yes.
Yeah, equality is a little bit more
kappa
precise.
is just B1
Yep.
divided by 2 to the power B1 over 2. Okay, so I can that's section 2.2. Notation. So basically, let me just summarize what I'm going to look at. So now, I can erase this green as well. Now, what I'm going to look at, I'm going to look at a similar problem. We have, again, two-dimensional cone, the same cone as earlier, but now we are looking at the random walk. Okay, so now we consider random walk as n, which is equal to x1 plus dots plus xn, and now I need to make several assumptions. So n changes from 1 to 2 and so on. And here, that's where xi, of course, id random vectors. Okay, now next thing, expectation of x1 I. That's the first coordinate of x1 of xi is equal to expectation of the second coordinate and is equal to 0. So xy is just x1 of I, x2 expectations are equal to 0. Also, we remove the drift. So the next thing are variance of 1I is equal to variance of x to I, and it is equal to 1. Okay, so we normalize immediately the random walk, and finally covariance of coordinates x1 of I and x2 of I is equal to 0 as well. Okay, so they are uncorrelated. Okay, so this assumption and this okay, so you can always subtract the mean, then you can always achieve variance if you wish. Now the last assumption is also innocent, because what you can do, well, even if these random variables are correlated, then you can multiply, well, you can do a linear transformation. Then, so this linear transformation are going to transform the cone into another cone, and you can achieve with this linear transformation that both of, well, new random variables y1, y2, which you will get as a result of this linear transformation, are interrelated. Okay, so you can always achieve it by the suitable linear transformation.
And this x1i equals x2i.
Well, yes.
It's not much point in doing a two-dimensional.
Well, unless you are in one-dimensional situation, yeah. But if you're in one-dimensional situation, you're already professionals, you know what to do from the first part. Okay, so you're not interested much. Okay, so that's one set of assumptions. So let's call them centering assumptions and centering and normalization. So I'm gonna need also moment assumptions. So I will make these right away and explain shortly why we need moment assumptions. Okay, so the first moment assumption that I need is this one. So always we need that expectation of modulus x I to the power 2 plus delta less than infinity for some delta greater than 0.
So, can you use a better pen, because the recording may not be seen well. Have you got a better one?
Oh,
I'll get one after the break.
So this one hopefully is better. Okay, so so we need at least 2 plus delta moments. So why do we need it? So I'm gonna use central limit theorem, but not just the central limit theorem, but central limit theorem with some rate of convergence, a so-called strong coupling. And to have sufficiently good rate of convergence, I need these extra delta moments. Okay. And yeah, so that's one assumption. And the second assumption is that expectation modulus x I to the power p less than infinity as well. So that's the second assumption. And you will see just in a few minutes why this assumption is needed. Okay, so we just p here is p1, so that's p coming from the eigenvalue problem. Okay,
So that depends on alpha.
yes, it depends on alpha. Oh, in this case, we know what p is indeed. So let me write this down. Because in two-dimensional case, we have an explicit expression where p is equal to pi over 2 alpha. Okay, so we have this expression indeed. Okay, so why do we need it? So to explain why we need this extra assumption, so I'm gonna quickly explain the strategy. So how can we approach this problem? Strategy. Okay, so that's our common idea. Let's try again.
So the ones on the left, they're all dead? The ones you brought?
I think so. Yeah, this one is
Is a bit better.
better. Okay, so so what's the strategy? So how can we try to solve this problem? So basically, the strategy is to use. So we want to use the central limit theorem with the convergence. So what we want to do, we want to replace our Brownian motion with our random walk with the Brownian motion. But when we do this replacement, there is an error, right? Because, well, somehow when you apply central limit theorem, even with the rate of convergence, still there is an error. So if you try to do this immediately, if you try to do it at step 1, so we want to replace the full trajectory by the Brownian motion, then the error that we're going to get is considerably large, because somehow it's the same as starting Brownian motion from here, for example, there or there. Okay, so it can be very large, it doesn't give you precise information. So our strategy is, let's wait for some time. Okay, so let's wait for some time, and then what will happen is that if we condition on the random walk to stay in the domain, the random walk will have to go inside the domain. Okay, so it will have to go inside the domain. There is a simple lemma explaining this. And then when it is sufficiently far away from the boundary, if we are here, now when we introduce this, so up to this point, we have our random walk trajectory. After that, we are going to replace random walk with the Brownian motion. Now, if you do some kind of error control here, what you will see, you are here, but what will happen, you are going to replace this random walk with the Brownian motion, but the error is not that large. So if you're far away from the boundary, well, you are more or less okay. So that's the strategy. So basically, what we will do, we will write probability that tau x greater than n as the integral of probability that tau x greater than some nu n. Nu n means that you are far away from the boundary. I will give explicit expression later on as nu n belongs to dy, and then probability that tau y greater than n minus nu. Okay, now if nu n is o small of n, and that's what we will, so you will see that's what happens. So in this case, then we can replace this probability tau y greater than n minus nu with probability tau y greater than n, and because well, integration goes far away from boundary, you can also replace exit time for the random walk with the corresponding exit time for the Brownian motion. Okay, so well, somehow if you think about this, if y is of course the square root of n, so basically here you will have nothing else but the functional central limit theorem, which will guarantee this. If y is a little bit less than square root of n, then you can use the rate of convergence for that. Now, well, suppose you have this. So what we know now is that probability that tau y be n greater than n behaves like kappa u of y divided by n to the power p over 2. Okay, so that's something that we know from the asymptotics, which I have just described. So basically it means that this is approximately equal to integral probability tau x greater than mu n as mu n belongs to dy times kappa u of y over n to the power p over 2. Okay, and again this is approximately equal to, so it's not rigorous, it's just explanation what will happen. It's approximately equal to kappa expectation. And here you will get u, well, I should have so everywhere it should be x plus mu n, s mu n, x plus s mu n, u
Denis,
x.
I'm sorry, it's all the time for us to make a break, but maybe more importantly, it's next to invisible on the camera. Maybe I'll fetch
Okay,
better
well,
markers,
I'll
and
just
then we'll-
finish
yeah,
these
and
two
then
lines.
we'll repeat this, maybe. quickly.
Tau x greater than n divided by n to the power p over 2. Okay, so that's an approximation, and I will discuss what it means after the break.
Thank you.